So that means some methods are probably better than other methods for this particular purpose, right? But how do you analyze, how do you tell which method is more accurate? So you have multiple algorithms. How do you assess if one algorithm is better than another? Get some data and see how do you measure up. So okay, so that's a very good point. Get some data. So can you come up with another algorithm that tells the computer how to get the data and how to measure up how good the scheme is? All right. Let's imagine you are working on some project and there is a numerical simulation that you can use to get to some result. And it may be much more complicated than evaluating a derivative. How do you come up with a way to assess is simulation 1 better or simulation 2 better?
Like approximate the derivative and then take a dt, jump derivative times t, like derivative times delta t.
One set of data.
So right, so the question here is actually to evaluate the accuracy of the derivative approximation scheme, right? So I see two of you are answering based on computing the error, which is very good. So the error here is defined as so this is I don't have the name, but I think is by your group. So the error is defined as, let me just write it here, absolute value. Don't forget about this, right? So this is very important. Absolute value of, for example, the error of the first one, absolute value of du dt1 minus the actual analytical answer. So here is actually a very interesting question. Is here we're assuming we know the analytical answer, right? So in this case, we can actually compute the error, but in general, we don't really know the analytical answer, right? So think what I'm doing here, how can it extend to the case where we don't know the analytical answer? So here we have the analytical answer, so we compute the errors, and then I have actually 3 answers here that I think are based on the I have 3 answers that are based on this error. One is the average of En square, and the second is the max max of En, and the third answer I get is the sum of En square. Okay, which one would you prefer to compare between one method and another? Yes.
Depends on what your application is.
Depends on what your application is, right? So that answer I would accept if the choice is between either average or max or sum or max, right? Some of the applications will care about the maximum error, some of the applications will care about the average error. But how do you choose between average and sum? Yes?
Choose the sum of the squares, because if you just take the average, maybe sometimes it overpredicts and sometimes it underpredicts. So then your average error might be 0 when actually your average error is like some non-zero value.
Now remember, my error is defined as what?
Oh, the absolute.
Oh, okay.
So what's the difference between the sum and the average? It's just a factor of n, right? Yes?
Yeah, I was just going to say it doesn't matter if you know what n is.
Yeah. Doesn't matter if you know what n is. But here is when I'm going to introduce a critical concept, is what we call refinement. Okay, so when you perform a numerical simulation, and when you try to assess the accuracy, it is usually insufficient to check the accuracy for one particular delta t. Right, so here what I did is I only did it for a delta t of 0.01, right? In general, you should check for multiple discretizations. And in general, if you have multiple discretizations, you have multiple n, right? You have different sets of points where you can evaluate the accuracy. So now, when you think of that, should you choose the mean or the sum?
Because it's independent of your value of n.
Yes, the mean is usually a more fair comparison. If you're comparing against two simulations with two different degrees of freedoms or two different set of points on which you can evaluate the error. All right. So usually, if you have one simulation that is use a lot of points to be trying to be more accurate, and another simulation who uses much less points, and if you do the sum of the square of the errors, it is very unfair to the more accurate simulation because it just has more points for you to compare against, right? So here, I would take absolute value doesn't have the problem, right? Only the sum or the mean has the problem. So to drive the points, I would compute the error 1 square. I think I have to do dot square in MATLAB because I want point-wise square. The mean of this. Yeah, so in MATLAB, I think I have to do the mean and mean. So that's just the, when MATLAB does mean, it only does it in one axis. So you actually have to either figure out is this a column vector or row vector, and say, okay, I want to do the mean over that particular axis, or just bluntly do mean over twice. You get the global mean. So the error. So the first. Did I do something wrong? That seems too large, right? So oh, okay. Again, it's a MATLAB problem. You can easily spot from the workspace. Okay, when I compute the error, I subtracted a column vector from a row vector. I ended up with a matrix of 1001 times 1001. So I need to transpose this in order to get the correct error. So that's a I kind of hate MATLAB for that. If you use Python or something, you don't really have problems like that. Okay, so yeah.
So woo Python.
Okay, how many people actually prefer Python to MATLAB? Okay, so that's what I thought. I've been kind of thinking about switching to Python for this class for a long time, but like still majority are more comfortable with MATLAB. So maybe that'll last for a few years.
The whole department should just switch to Python.
Okay. Anyway, so this is the mean squared error of the first one, second one, and third one. All right. It's pretty clear the third one wins by a large margin, right? Different orders of magnitude. Although all of these are good, okay, but the third one is actually a lot better. Yes?
What is if you have the absolute value, what is the reason for squaring the error?
Oh, there is no reason for taking the absolute value before squaring the error. It's just you get the same thing. If you take the mean, you get different things. So there are actually more than these two ways of computing, of estimating the error. You can also estimate the error as the average of actually just the en, right? So these two methods, so don't do this. These two methods actually requires you to take the absolute value. Otherwise, you get the wrong answer. The average of a square, you don't really have to. And by the way, we usually take square root after you average so that you get the same dimension, you get the same units as the solution itself. All right. Otherwise, your units are different. So when you compare the error against the actual solution, when you want the relative error, it's better to have the same units. All right. So here, after you take the square root, there are still different orders of magnitude.